Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. Well, Madhur, thank you so much for joining the podcast here today. We've known each other for some time. You are a professor at the University of Virginia in computer science.
That's right.
I'm a proud alum of the University of Virginia.
Go Who's.
And you are heavily involved in autonomous vehicles, in particular ones that go really fast, which is really cool with Cavalier Racing, right? So
That's right.
I think you hit a speed record. So let's just dive right into it. What's going on with autonomous racing in the world, and what are you doing with this?
Yeah, thanks, Paul, for inviting me. First of all, it's always a pleasure, having a chat with you. So yeah, I mean, autonomous racing is not science fiction; it's real. Let's just start there. That we have full-scale, fully autonomous Indy racing cars, which university teams are competing in like a battle of algorithms. And this is a field which probably did not exist more than 8 years ago. And I was heavily involved, one of the crazy people who was advocating that this should be a thing. And it's just immensely gratifying to see this vision, come to pass, and it's now a reality. So, as you said, I am the team principal of UVA's Cavalier Autonomous Racing Team. We are a team of graduate and undergraduate students. It's really an extension of my research lab here at UVA. And so we compete in this global competition called the Indy Autonomous Challenge. This started actually in the middle of the pandemic in 2019, 2020. And we did a year or two of simulation-based racing. There were around 40 university teams. And it had the very same mentality like what you are familiar with the DARPA Grand Challenges, which are responsible, in my opinion, for the entire AV industry's existence to a large extent. So that was very much the idea, what is the next frontier? Not like we've already solved autonomous vehicles that we need a new frontier, but it was supported by the government of Indiana, and they had ties with the Indianapolis Motor Speedway. And they visioned that, what would it take to have full-scale Indy race cars compete in like this global competition.
So if I could, so these cars, just to be clear for everyone, these are full scale racing vehicles. Can you describe like the vehicle platform just in a nutshell, like the size
100%.
and what it's like? Yeah.
So this is a real full scale car. It's not like the RC car you see behind me, but this is based off of the Delara IL-15 Indy Lights chassis. So it's not the full-scale Indy race car. It's the league below Indy Racing, which is called Indy Lights. Or now I think they rebranded themselves to Indy Next. So this is the Delara chassis, the same one that the human drivers race in. And there are 10 clones of this car. It's not just one car. So there are 10 competing universities in this competition. Everybody has the same car. This is a gasoline-powered Honda engine, 490 something horsepower. And it was retrofitted to become autonomous with a drive-by-wire system, and with all the bare bones and the electronic controllers you need. And that itself was a monumental engineering effort in the early part of the competition. But the idea was always to have this, proving grounds where the emphasis would be that the only way you win a race is by designing this AI driver. There is no room for a driver in this car. The cockpit is just packed with our computers, with 360 solid state lidars, with multiple radars. We have redundant GNSS systems. We have 6 cameras as well. So it's really a research platform. I personally would see this as a $1 million research lab on wheels. And the car is not here in Virginia. It's secured safely and maintained by a professional racing crew in Indianapolis, in a garage in Indianapolis. So we go to the car as a team to work on it for a few weeks in a year. We don't have a ton of track time. It's pretty expensive to rent out these NASCAR and Indy racetracks. So we do a lot of our algorithmic development in house, and then we show up before an event, maybe a few weeks before an event. We get to see the sim to real nuances of, is the car behaving as we expect? And we do iterations every single day. Every practice lap is a ton of data for us to see what is going on. And so this is basically what the platform is. And
And then you put that platform then now, so all these 10 groups or whatever convene at a location. Like, is it all the same location in Las Vegas at this point, or is it different locations across the country? And then you race, right? Is that the
yeah,
gist?
yes, that's the gist of it. So the first race was held in 2021. It was held at IMS, home to the Indy 500, racing capital of the world. Just being at the track is just surreal. Just for me, my students, like, we treat the track as if it's our lab. So we get to stage our car and work on it in the same Formula One garages at pit road. And during the practice session, we roll out the car, we set up a tent and bring out our computers right next to the pit wall. We tether to the car. And so then the race is held there. The very first race was a time trial competition. The vision of this entire league is always to try to get close to what humans can do. The humans can do some pretty crazy, incredible things in race cars. In this chaos of 30 drivers at Indy 500, that's way, way down there. We're not there yet. So we had to start with a simple single car time trial, go as fast as possible. And that was the first race. There was $1 million prize on the line for 10 university teams. And so I think at the time, maybe 5 teams were able to put a full lap or multiple laps. There were many problems that other teams had with hardware, software. And so in that race, we emerged as the top American team. We didn't quite make it to the podium. There were 3 European behemoths in autonomous racing. We can talk about them later. But then the model became that let's take this competition to different racing tracks. So we've raced at the Las Vegas Motor Speedway on 3 occasions now. In fact, we always piggyback with an event which has ties with CES, which has every January it's held in Vegas.
Mm-hmm.
So there's a race at CES, and then we have raced at Texas Motor Speedway. We've also tried to race at a road course in Indianapolis called Putnam Park, and then there are some smaller practice tracks where they are only like a half-mile oval. Where we race in, which is also in Indiana, called Lucas Oil Raceway. And then this year, which is what the record came from, we had a race on September 6th. This is the second time we returned to IMS, so pretty monumental occasion, I would say. And so on this race, on this day, our car set multiple track records. So we got the lap record for the fastest lap, which is 52.628 seconds. I know it by heart, probably for 2.5 miles. So that's like an average pace of 171 miles per hour. And while doing that fast lap, we set a top speed of 184 miles per hour while we crossed the start finish, which is a new world record for the fastest autonomous speed on a racetrack. And in also doing so, we became the first team, American team, to ever win the Indy Autonomous Challenge. Yeah, so it's
That's
pretty.
fantastic.
Yeah.
That's wonderful. I mean, and that's amazing. 184 miles an hour,
Yeah.
which just brings me to sort of maybe a sidebar philosophical question. We human beings were not designed to go 184 miles an hour as humans, right? It's like, what we can run. I don't know. Well, Manute Bol can. Was he the guy who could run really fast? Is he the right
Yeah.
guy?
Okay.
Yeah. But he can run really fast. But like, what do we got? Like 5, 10 miles an hour, or 15, something like that.
Something like
Um,
that. Yeah.
that's like, we don't have the sensors in our on our body to like, we've got eyeballs, we don't have the muscles obviously to propel us at that speed. What have you given any thought to like what's special about human race car drivers that enables them to get in that vehicle? What's different about them, or what skill have they developed that enables them to drive a car 185 and 184 miles an hour?
Yeah.
The human side. Have you
Yeah,
thought about that?
and I have deeply thought about this. I've also had the good fortune to meet some of the Indy race drivers and pick their brains. Um, so first of all, I agree. I think the only correction I make is the average humans can do what these specialized racing drivers can do, and it's astonishing to see that they basically don't lift off in the middle of a turn. And you look at the telemetry, and they are just working at some incredible zone. So I was always curious that what is it? Where is the gap between our interpretation from gathering sensor data from the wheels and the engine and trying to push the limits of the algorithm versus the humans? And so every single human driver I have spoken with, the lowest common denominator comes down to the following. They are very technical, and but they at the end of the say that I can feel the dynamics of the car. I can know. So they have an instinct for a feel that the car is understeering or oversteering, and are they near the traction circle at the limits of their GG diagram? And so then the question is, how do you feel, right? So what is it about their brains that is allowing them to feel? Well, one component is that they're physically in the car. They can see the responsiveness of what they are commanding and how the car is behaving, and the vibrations coming in from the seat and the G forces that their brain feels. And if you get down to it, most, if not all of these race drivers, they got a very early start when they were uh, little kids, like 6, 7 years old. They were karting, and they were already sort of, experiencing motorsports, maybe as a hobby before they turned professional. And so over the span of their careers, they have developed instinct, and they have developed this innate ability to look at a very chaotic situation and how to analyze risk in this uncertain motion planning problem that they have to solve, how to basically understand the physical limits of steering and traction and pedal control and braking dynamics of the car. Now, the sport is also evolving because the technology evolves. And to me, my fascination with Formula One racing was always, this is the most technically advanced sport. So as an engineer, how can you not admire what these drivers are doing in these incredible machines? So I think at the end of the day, it this is a prime example of the problem in artificial general intelligence. This is, what's being debated every single day for the past decade now, and especially in the last 2 years. And I kind of find it amusing sometimes when people say that ChatGPT and a large language model is very close towards solving artificial general intelligence. And I get where they're coming from, but I look at that, and I'm like, no, like, these models have no understanding of really the physics of what these humans are able to do, the reasoning, the long term, short term, rapid decision making at millisecond level, what to pay attention to, because there is no luxury of time to pay attention to everything when you are racing at 230 miles per hour, which is what real Indy race cars go at. So I
That's
think,
Yeah, that's interesting. I guess
yeah,
because so just a point there, yeah, because ChatGPT and these models just rely on data that can be fed to them from like files and documents, right?
right, right,
But like these race car drivers, part of what they're sensing, I would think, based on what you described, is the feel, like the inertial inputs, basically that are coming into their body, maybe
body,
through different sensory points along their whole body. I mean, maybe they feel something in their hips versus their upper body versus their lower body, and that maybe that information affects what they're getting. So they don't have just one like sort of IMU. Like we have many IMUs in our body, right? Like
yeah,
measuring inertial forces all over. And like that kind of data is clearly not being fed into
Yeah, I mean, we are
GPT.
trying, right? Like
Yeah.
our proxy of a driver is we have multiple inertial sensors which try to measure the dynamics of the car. We have sensors in the tire which the human does not have access to, but
Yeah, there you go.
we actually have access to tire pressure, tire temperature. We have sophisticated physics models for tire slip angles and all of that. So we're trying to create the AI or the coding for approximating this feel that these drivers describe, but it's very difficult. And I feel the just to linger on this, physical the importance of physical AI for just a second. Um, if you, in my opinion, what has happened is that these large language models they are based on a very clever transformer architecture, the GPT architecture. And as you correctly pointed out, to be able, so I am impressed by what GPT can do. It can do images, now it can do video as well, and text for sure. So there is definitely some very clear signs of intelligent behavior. We don't really know why these behaviors emerge. That's one problem. But the thing which is missing is that today's AI, as advanced as it is, it's just residing in the virtual world, right? So you can use these AI tools to manipulate text, images, video, digital content, right? They live in the Twitter sphere and the metasphere, to so to speak. And they are very effective. There are some concerns as well on misinformation and all that ethics of AI. But they are certainly not living in the physical world. When you and I grew up, our brains have a mental simulator, physics simulator inside of us that when we drive, I am not actively trying to run a simulation, but my brain is predicting every single agent's motion. It's figuring out who to pay attention to. It understands the physics of the world. I don't try to linger in the blind spot of a huge truck because it has large momentum and it'll take me out in one swerve. So we understand the world model or the physical model of the world. We simulate it, and that's how we plan. And I think the models today don't have that embodiment. They don't have that physical being. And this is why I feel robotics and AI is the frontier. And robotics is the ultimate uh, missing piece to enable these models to have agency over the physical world, to interact with the physical world, and build
Yeah.
these mental models,
The
which is what driving is about.
the sensory information and for sure too. And it's interesting you mentioned something just now that you can also add sensors into the wheels, right? Like IMUs were inertial measurements that like a human wouldn't have. So there's this classic, I don't know if it's a tension, but kind of two there's many worlds, many ways of thinking obviously, but there's sort of the bio inspired approach to thinking about how to build machinery, like hey, let's see what humans do and like try to replicate or enhance that. Then there's the fact that, well, hey, we've got this technology. We've got things like LiDAR that we as human beings don't have. Our eyes are kind of maybe more like cameras than anything else.
Right.
But we don't have LiDAR and we don't have radar. Why not use that? Because if we had that, we would be like, we would be like some sort of superhero. Like
Exactly.
and
Exactly.
and so leverage this technology and the same thing that you just mentioned by adding IMUs into the wheels. What kind of so those must demand different algorithms, right? Because one, the bio inspired tends to push us towards, it seems, neural networks and maybe and other types of AI techniques that we've modeled off of maybe human behavior. But then on the flip side, by adding these other sensors in and other technologies in, it's more of a control systems type driven or determinism, real time determinism type methodology for more mathematical, I should say, than sort of bio inspired.
Yeah, that's 100% on point. And if you one of the top questions we always get asked, not just me, but all the teams, is like something along the lines of how many AIs are running on the car. And internally, we kind of chuckle at this. I know where this is coming from, but the that distinction you made between, like neural network based architectures, which are heavily data hungry and which have proven to be successful in many non-physical domains as of now, they still have a place in our stack. And we can talk about kind of the classical perception planning control problem in robotics and how that pertains to racing. And so our car uses or needs to know, if we want to run anything at triple digit miles per hour, you cannot ignore the knowledge of physics. Now, the difficulty is not so much that we don't know what the physics is. The difficulty is that it's so difficult to model it correctly for a real engineering system as complicated as a race car, because of the reasons that you just said. Like, we know what my boy Isaac Newton has prescribed. It has to follow the laws of physics, but uh, to be able to get that correct mathematical model, you need to estimate the internal state of this complex machinery. Things like, the normal load on each wheel, the drag force, the slip of the wheel, just the rotation of the car, the lateral acceleration, longitudinal acceleration. So these are well-known, well-studied pieces in vehicle dynamics. I'm sure there are courses and reams of books written on this topic. So, but the difficulty has always been, how do you take this known model and how do you actually tune it or tweak it for the system you want to control? And so we do use model based control approaches, which are at the end of the day using an internal, well tuned model to predict what is going to happen in the next 2 seconds and use that prediction to steer and adjust the throttle appropriately and safely. Yeah, it's the difficulty in learning these models. And so once again, there is room to do some neural network stuff here. And in fact, we have a couple of students whose dissertation is on this exact problem, that how do you make sure that you can learn from the data, because at the end of the day, your model has to agree with the reality and the real measurements from the car. So can you do something that can leverage this learning capability of neural networks, but ensure that they respect the known physics of how this robot has to behave? So it's like
Yeah.
the physics constrained or physics informed learning is one of the thrusts in my of research in my group. And autonomous racing is a very good kind of application case to conduct this research. So it is a mix of physics based and pure, neural network hybrid kind of models that we run on this car. When we talk about perception, that is where you have most kind of traditional deep neural networks for lidar detection of the opponent, for bounding box in a camera. We were using geometric based methods for our radar pipeline, but now we are also trying out some neural networks that can cluster radar points together and basically get us to know where the car is. So in racing, it's very different perception problem than urban autonomous driving, because we don't have the heterogeneity of pedestrians and cyclists and traffic signs and lane marking. So it's a different problem. And right now, the problem is challenging only because we are moving very fast. So what the kind of problems we are solving is, how do you detect reliably under a lot of uncertainty, under a lot of vibration of the sensor? So your data is kind of not clean anymore.
Yeah.
But the future of this autonomous racing as a research field uh, is having more and more agents. And so it will become, perception will also become a challenging problem. Right now, it's maybe not the most research driven problem. Most of the research in racing I would attribute to localization, to motion planning, and to control of the car at these high speeds. So knowing where you are on the track with the decimeter level precision at these very high speeds is just crucial,
Yeah.
because
Yeah.
it's the difference between being on your race line and into the wall at Indianapolis. So those are where the most of the research problems lie right now.
Yeah, well, I'd love to peel away a layer of the onion on some of this, because you're
I know.
what you're doing is so fascinating. So to that end, like, let's just start. It helps me to kind of sometimes start with the control system, and like, so there is the car, which you described, and I guess what's sort of the mechanical electrical structure of the steering? Is it a I guess it comes from a third party. They integrate the steering, or
Yeah.
did the teams integrate their own steering?
No.
What is the steering mechanism? Is it redundant?
Yeah. So let's kind of get into the guts of the the autonomy side of the hardware rather than just the algorithms. So when these cars were provided by Delara to the competition, um, there is a group at Clemson University, uh, not far from Virginia, and they have a program. It's like a graduate program at that university where every 2 years they design a new crazy prototype autonomous vehicle. So they do some shuttles or some something for the defense. And so one of those programs, their task was to design an autonomous race car. And so the organization which put together the Indy Autonomous Challenge, they invited some of the professors like myself to a workshop, and they put us in touch with this team. And together, over multiple years, we designed the kind of the interface to this race car. And so the car uses a drive-by-wire system essentially. And originally, it was, I think, a drive-by-wire system from Schaeffler. That was what the steering was. And so again, that was like the first thing we did. So just the engineering itself, as you know, also has its own iterations. So what we designed in 2021, in the very next year, we were already kind of critiquing that, oh, this is flawed, this doesn't hold up. Because these components were like I'll give you an example of our main computer. It's like an embedded PC, Linux running machine. That's a Linux box. It's very high performance, but it's not designed in a ruggedized manner to be in a high vibration racing environment. And so you wouldn't believe it, but uh, we were having issues where at 120 miles per hour, there was so much vibration on this computer that the CAN card at the PCI became loose, and you couldn't
Oh yeah.
basically control the drive-by-wire system, and you had crashes there. So we've
Right.
learned some expensive, expensive crashes to learn from these mistakes. But we have a drive-by-wire system. The engine of this car was also modified. So this is not the same engine as is what is used in the Indy Racing series. It's built on the same Honda engine, but it's customized by again a business called Four Piston Engines based in Indiana. They customize it because we wanted this engine to be more stable and low vibration at at low RPMs. These engines are designed to run at like crazy 7,000, 8,000 RPMs all the time because they only run them for a year at most, and then they are end of life. Well, we are not a professional racing team. We needed like many, many years of life from this engine. So it was kind of toned down a little bit. Then there is the electronics inside the car, the power distribution system, the entire kind of internal chassis, how the ECU, the steering ECU on the car, the braking ECU on the car. So those were all initially off the shelf, and over the years, that engineering has also improved. But it was a mix of academics and the teams, which initially I would say CAD designed this, but then they, I think, outsourced the actual engineering of the vehicles to put the pieces together to a company at the time, and who created 10 different identical cars. And
I see.
so yeah, there is a, but now, now I think the car has gone multiple, you could say, iterations of improvement or refresh. And the current version we use is very different from what we were racing in 2021. Um, it has better sensors. It has a more responsive steering motor. And it has basically a lot of the things have been bespoke and customized to the task of autonomous racing rather than trying to see what is available or trying to get some hardware from a sponsor and doing our best to make it work.
Got
Um,
it. So
yeah,
so the steering motor, for example, which has now been there's been some iteration. So that's, connected, I guess, either to the drive shaft or the rack and pinion system. I don't know.
right.
But
Exactly.
but like is that just an off the shelf motor, or did it have to be specially made to
I think
kind
the
of
motor
deal
is
with?
off the shelf. The motor
Okay.
is off the shelf, but it is very high performance. One of the things we noticed was, so far we've only raced mostly at oval tracks. So kind of you only mostly have to turn left, except if you're overtaking someone on the outside. But we are transitioning to road courses, and it was clear to all the teams that the response rate of this previous motor wasn't great. There was too much actuation delay. It wasn't that responsive. So we needed more precision steering. We needed more precision control over braking. So rather than just like one global brake command that goes to an ECU, teams want to play around with front bias and rear brake bias, as actual racing teams also do. And so,
Okay.
so
So
we have, yeah.
describe that for a little bit, because I don't think everybody. I mean, I certainly don't like. So it's not just a brake. Well, there's a brake pedal, I guess, but you're controlling now different braking points on the vehicle.
So there is not even a physical pedal in the car. So
Okay.
it's all it's hydraulic kind of braking as far as my understanding is concerned. And so there is a braking ECU. And earlier, what used to happen is we, as the autonomous team, we were very, by the way, shielded away from this low level stuff, right? We wanted, and for good reason as well, because I don't think all the CS students knew what they were doing when we were exposed to these low level
Sure.
kind of state machines. And so earlier, we used to just command some global brake pressure if we wanted to slam on the brakes, and the ECU would decide equally distributed to the brakes. And I think the capability was not there to do anything different.
Right.
And now the Indy Autonomous Challenge engineering team has modified it so that it's a little bit more true to real race cars. And so on a real race car, based on what the car is doing. So if you are going into a bank turn, or if when you brake, essentially you change the load on the wheels, right? So here, let's geek out for a second on this, okay? So it doesn't matter if a human is driving or a AI is driving or you are rolling the car will only move forward based on the contact patch that the tire makes with the tarmac. That's basically what it boils down to. Doesn't matter the causal reason for what makes the contact. So if you can understand and control how these Bridgestone tires can make contact with the tarmac and not lose traction, you can go as fast as possible and you can do as crazy maneuvers as possible. This is what staying in the limits really boils down to in racing. And so, uh, to understand what the contact of the tire is to do, you have to have models. These models need to know what is the vertical load on the wheel, what is the lateral load on the wheel. So where do these loads, the forces on the wheel, which is what I'm calling these loads, where do these come from? They come from the motion of the car. So the acceleration of the car, the deceleration of the car, how you steer produces lateral load. How you accelerate and brake produces longitudinal load on the car. So when you just brake uniformly, you are kind of when the car brakes, you feel that push going forward. So the rear wheels are basically getting released. They are getting a little bit
Hmm.
lightheaded, and the load is on the front. So if you are turning and braking, it's very risky because you are already overloading the front and you are putting some lateral stress as well, so you can spin out.
Yeah.
So if you can be more strategic in what kind of braking pressures you demand on the front versus the rear so that your car can be basically in the equilibrium state at all times and still go fast. It's the most like beautiful zone to be in, where you don't run the risk of losing traction and spinning out and hitting the wall.
So
So
did the human drivers have that control, or is this
yes,
just built
yes.
into the ECU? So they can distinguish. I've never driven a race car, so they can distinguish between how much pressure I'm going to give on the rear versus the front wheels. Is that two different pedals or something? How do they control that?
Very good question, right? So the if you watch Formula One or I believe even Indy broadcast, and you have the driver cam where you can see their steering wheel, you have a gazillion different knobs on the wheel, and as insane is it to just keep it together and not go off the track, these guys are changing both the engine modes and braking modes turn by turn at times in some of the
Oh,
tracks.
wow.
So there's a little knob, and this the driver knows that for the next sector, this is the setting of the brake. So they will tune to some setting on their steering wheel with a thumb or some just a push button, cycle through some settings. That's what that MIDI computer in front of them is for. So they can make these adjustments. Now, of course, what they can do is regulated by all the racing organizations. And most importantly, they are the ones who have to make the adjustment. A computer cannot make these adjustments on someone's behalf, on their behalf. So the team cannot issue a radio signal lap by lap or turn by turn, but we can, right? Our race car is autonomous, so we can do whatever we want, um, and a computer is the driver. So yes, absolutely, the humans are also tweaking these brake biases, is what it's called. And if you ever want to experience driving a race car, we have a racing simulator, like a Formula One simulator. That's actually what we used before we had the full scale car.
Oh, wow.
My students took the Formula One game from EA Sports or Codemasters, and basically we converted this real racing game into a simulator. So we
Oh,
could have an AI look at the imagery and issue some Python commands to drive autonomously. And this is how the research side of racing started for me before we were playing
you should
machines.
hook up a little, coin buy I mean, you could, charge money for that. People become a buy popping quarters or maybe dollars these days into it.
Yeah, yeah, not a
Um,
bad idea.
no, that's cool. That's very cool. So it's interesting though. So now do all the drivers have this do all the vehicles then they must all equally have to have that capability in the human driven situation because otherwise there's an unfair advantage across drivers or do they, are some vehicles don't have that capability and some do?
Yeah, so I think in real racing, like so my confession is I race Indy autonomous cars, but I am more into Formula One as a motorsport. So I can speak on how my understanding of F1 human racing is. There is at every season there is basic. What is Formula One? Formula One is the name for a set of specifications that you must meet. That's the formula. And so every team in every season can design a car, but it cannot violate any of these specifications. So this is the kind of their way to enforce a level playing field.
Mhm.
But as long as you are within the specifications, you have the engineering creativity to improve some aero design, to do some engine improvement, to do some design of the car, add a little, air duct here or something over there. This is where all the real Red Bull, Mercedes, McLaren, they get their competitive advantage from. In autonomous racing, this is largely about the autonomy, the AI.
Right.
And so all cars are the same. They have
The
the same
same.
hardware, the same engine, the same tires, even the same setup to a large extent. How much camber and how much kind of the suspension setup of the car is. It's very uniform. The same computer, the same sensors. But in real racing, um, I don't think that every car necessarily is identical hardware. In fact, uh, that would be interesting to watch because then that
Yeah.
would be a true test of driver skill, right? Right now you see that okay, this person is dominating the sport for many years. Is it because their car is just better than everybody else, or is it can they go to another team and show the same thing? So I get that attraction as well. It's what drives the sport. It's very personality centric of these drivers, as it should be. They are literally putting their lives on the line every single race. uh, but yeah, I think in our case, we are more focused on everything is uniform. How well can you program this AI capability that can overtake another car? So what I did not maybe touch upon yet is our Indy autonomous races are not just single car doing laps. We are now at a stage where there are two cars on the track and that they can take turn autonomously overtaking each other, increasing speeds lap after lap after lap. So
Gotcha.
So we are not quite as sophisticated as a real field with a dozen cars, but that's my personal goal to sort of push the field in that direction.
No, that's cool. And so that's the brake, and then the throttle, I guess, is it's just open or levels of throttle, right? There's no variation there, or is there something different about throttle than a
No,
normal
we
car here?
we we it's very similar to a normal car. We have drivetrain data from the entire engine. So
Hmm.
they take the car, they put it on this dyno testing, which is a fancy treadmill for a race car,
Hmm.
and they spin the wheels. They gather engine RPM versus torque data for different gears, and so they share this data with all the teams. The teams then can use the data however they want. Okay, if you want, you can not use the data at all. Just do some PID on the throttle. And in fact, this is what we used to do in the very first time. Right? We are not. I'm not. I don't have a suite of engineers who are just dedicated to dynamics. These are students who are working on this. So that's how we started as well. Just simple proportional integral derivative tuning. We want to go a certain speed, look at where we are. If you're going too slow, give it a little juice. If you're going too fast, slow down a little. Just do PID on some reference.
Yeah.
But now we are at a stage over the years where we have models for the drivetrain. So we can actually command based on the current state of the car, we can compute how much acceleration do we need and translate that acceleration into a torque request and then figure out what is the right gear that we have to be in and what should be the throttle percentage that we demand from the car to
Oh,
meet
so you're
that.
changing gears too. So there's
Correct,
different
correct,
different gear levels. Okay.
correct. We are cycling through 6 gears on this car, and so N- I think after 5 years of doing real world racing, many of the teams are finally now in the interesting portion of the autonomous racing era where we are we have the capability to go fast. So now we can finally start unpacking things that we were not modeling before, like aerodynamics was
Yeah.
not really a big thing. But you don't see our race cars drafting close to our opponent and then wearing out. That's just first of all too risky. We
Yeah.
don't want to wreck this huge car because I'll get the invoice of the wreck. But I think we are getting to that point, and that's why it's such a extreme problem. It's such a fascinating, rich problem to push the limits of every single piece of autonomous driving.
That's fascinating. I mean, and so that I mean that's the control system, and then you're sending what's called, I guess, CAN bus messages
But
to these things to control that at a certain rate. Like, what is that rate, by the way? For
yeah, I think our motor, the steering motor, is pretty responsive. We can issue commands. I would want to say nearly like 150 hertz or something along those
okay,
lines. Our controller can run at 100 hertz or close to 100 hertz. So sometimes it can drop based on so because we don't have too much compute available. There's only certain amount of CPU, and
right.
that itself is an optimization problem that we have to engineer. So we are doing the algorithmic development, but autonomous racing is very much about software integration and software development and writing efficient software as well.
So that's
Uh,
interesting. So
yeah,
it's a half a millisecond to 1 millisecond kind of a rate
out
at which
feedback.
you're
Yeah,
so and you're but I guess are those commands coming from the Linux computer?
correct. There's a
So
DSpace computer on the car, which is stack runs.
so will Linux, I guess Linux is not real time.
It can
Uh,
be. There are some extensions where, so there
okay.
are some commercial versions which are basically Linux kernels, but they have support real time. We are not using one of those versions. We use Ubuntu,
Okay.
and we use ROS too. That's what my racing car runs. I think it has some support for real time performance, but I doubt how many teams actually have a real time kernel running on their
Right,
machines.
like QNX or VxWorks or the
Exactly,
popular
exactly. Yeah,
operating
yeah,
systems. So
yeah.
in that sense, how is it it's not guaranteed then, because I know you've done a lot of real time, it was your some of your PhD work was in real time uh deterministic systems. So like I guess you can't guarantee then that it's going to get a command every millisecond then, right? Is that right?
That is correct. So the way we circumvent this lack of guarantee is that if perception, planning, and control were the three pillars which move the car, the fourth pillar is our safety sort of fault tolerance architecture of
Right.
how we basically bake redundancy into our development as well. So, the only reason why any team feels comfortable pushing the car is because we have the confidence that if something were to go wrong, if the GPS quality drops, or we lose RTK correction, or something fails, or we lose connection to the drive by wire system, we know the car will be able to figure this out. It will catch this exception and come to a slow stop, or will safely come to like a what we call a graceful stop. And so it's actually at the end of the day, this confidence. How much confident are you in your coach, right? So you can be as creative as you want in your perception, in your fancy planner, in your model predictive control. But like you said, if it's a piece of raw software which sometimes can fail. There is a DDS architecture which gives you some data quality sort of loose assurances when you publish and subscribe to the information between different modules of the code, but it's not real time guarantee. And so we have to uh, account for that in our safety architecture. So again, we've written papers on what the safety architecture looks like, what can go wrong, what are some node health monitoring tools, data health monitoring tools, what kind of contingencies do we bake, what kind of multiplexing should we do if you have multiple signals coming in, which are surrogates of the thing you want to measure. You should check each one of them for their quality before you just fuse them together into something which is
Gotcha.
critical. So,
Now the drive-by-wire system, does that have something where if it doesn't get a command
yes,
within a certain amount of time, the drive-by-wire system will, I guess,
yes,
stop the vehicle or slow it down
yes,
or something? Or
yes. And so one of that system is called Raptor. It's a ECU, and there is a pretty complex state machine inside the Raptor, and it's always has like a heartbeat established with the main computer. And if you were to lose that heartbeat, which essentially means that something is wrong with the connection or messages are not arriving with the expected latency, then that state machine will kick in and it will basically say something is wrong. I'm myself just going to supersede your commands and bring the car to a stop.
so if you miss, like, if you're supposed to send the command every millisecond, let's just say, and you miss 1 millisecond, it doesn't just stop, it
No.
just slows down. But if you miss 10 milliseconds, is it
Yeah.
just slowing down more or is it stopping, I guess?
Yeah, so this is kind of up to every team how much risk
Okay.
tolerance they want to have. If you feel that whatever is the reason for this misbeat is recoverable, then maybe you have a larger. It's called like a leaky bucket approach. How many consistent hits do you have to see being missed before you raise the alarm and the car should stop? Because
Right.
remember, this is at the end of the day a competition. We compete, and stopping when we didn't really need to stop would be basically giving up our run during the competition or giving up practice time on the track, right? So uh, we do the right thing. We don't want to recklessly put the car in any situation where we don't have control over it or we don't know where we are on track. And so it's every team can decide this how much risk they want to take.
Sure.
Yeah.
Sure. And is there any feedback from some of the teams or, whatever, as to how much sort of like if they're using a non-real-time system, it contributes to slowing the vehicle down? Because I guess the question is, if you switch to a real-time system and you can guarantee determinism, does that help you increase the speed of
Yeah.
operation of the vehicle?
Yeah, I think short answer is yes, and every team, including my team, wants to go to that direction. It's just that we haven't reached that point yet. I also think that as we introduce more complexity in the race with more opponents, these things will become even more important, not just for control, but even for our, planning closed loop behavior
Yeah.
and perception closed loop behavior. So yes, it will not only make us go faster, but it'll, I think, make us be more safer. on track if we switch to a real-time operating systems.
Yeah, interesting. I mean, it's funny because real-time operating systems, as you probably know, it doesn't mean fast. It means just
It just means, yeah,
determinism.
yeah, it just means you have some guarantees, or you have some algorithms which ensure that the scheduler, which is scheduling these jobs on the processor, is going to do some best effort thing to make sure that every process meets its deadline of some kind. Yeah.
And it could actually so it's like this catch 22.
Yeah.
The real-time operating system might actually operate slower than the non-real-time operating system, but it's deterministic.
Right, right. So
So, in
yeah.
terms of how you're able to do things. So it's interesting. But that's interesting part of this control system. It's fascinating. So like, the sensors are of course at the other end of the
Right.
other side is there's controlling it, and then there's sort of getting the information in. What kind of you mentioned some of them, but can you kind of list the key sensors, low level, high level that you kind of use?
So yeah, we can start from kind of top to bottom. So the outward facing world perception sensors that we have are three luminar lidars. They are solid state lidars. They almost give us a 360 field of view. There's a little blind spot because we don't have a rear facing lidar. So we have three of those. We have two radars from, I believe, Continental. There are 4D radars, one facing front, one facing behind you. Then we have six cameras. They give us a pretty good at overlapping 360 field of view, side, front, back, uh, and so those are also pretty good Mako Allied Vision cameras that we can control with software to a great extent. Then our car has, I would say, three different GNSS systems. Two of them are Novatel GNSS systems. They are two because we need redundancy, because many teams still rely on these satellite corrections for precision localization, which is what RTK is. And we also have another GNSS system called Vector Nav,
Hmm.
which I think is used in like jet fighters and aerospace. So it's also very precise. And so this is all of the sensors, I would say, which we rely on to localize our car and to perceive our opponent and figure out, what is going on the track. Then on the car itself, there are on the body of the car, which I would call the state sensors. There's a lot of those. We have entire CAN messages, which describe wheel speed report, or everything there is to know. So every Bridgestone wheel has an array of, I believe it's 16 temperature sensors throughout the plane of the wheel. So we can go crazy and model, some thermal Pajeca model for the tire if we wanted to. We have pressure data from the wheel. We have primary, secondary feedback from the steering motor. So we can always keep an eye on, here is what we are requesting the steering motor to do, and here is what the motor is telling me what it is doing, and levels of redundancy over there. The same thing for braking. We have, brake pressure data from every wheel. We have strain gauge data at every suspension so that we know the normal loads, and we can use that into our own state estimation. Um, we have a ton of drivetrain data. This is an engine, like I said, not an electric vehicle. So we get oil pressure, have to monitor if the coolant temperature is too high, we can't race. We have to monitor the oil pressures. We have RPM data, like we said, throttle, gear data from the car. So we also have some torque sensors which were introduced. They can actually give you some approximate measurement of the torque the engine is generating. But I think right now my team hasn't really dived into using them. We also think they need some calibration. So pretty dense set of sensors to play with to do
Yeah.
state estimation of the car. Our car lacks, I would say right now, aero sensors. I would love for my car to have, what is it called? Pitot tubes, right? So we can measure, how much aero the wings are generating and even be more precise. But we're not complaining. There's too many sensors, and we have to do a lot of signal processing and perception to ingest all this data into some state estimation and
And
figure.
you're using did you say you're using one computer to get all this information? Or are you using more than one computer?
I mean, there are little mini ECUs scattered over the car, which maybe, that there might be a single ECU which takes all the data from the suspension and the wheels and then passes it to the main computer. But yes, there is one computer which runs the Linux autonomous algorithms
I
that we
see.
can directly control.
So the cameras, are you using those, is that just for logging, or are you actually getting data from those and trying to interpret the camera
No, no, no.
data?
These are. Yeah, we can run with all six cameras. This computer has a pretty beefy GPU from NVIDIA, and we can run all three lidars, all GNSS, two radars, and six cameras if we wanted to. Um, Now it also depends upon just running them takes compute, but now on top of that, you want to run some deep learning model or some Euclidean clustering algorithm that takes more compute. So it's a trade off. Like I said, my team has figured out that we mostly switch on the front cameras and the rear camera. We haven't really relied too much on the left and the right cameras yet. And it's also partly limiting because the CPU on the computer we use isn't the most powerful. It's like, 2 point something gigahertz CPU, and in the next incremental improvement, we'll get a little bit more horsepower on the CPU.
Sure.
We can run everything. Yeah, we can run them at real time at runtime. You touched upon logging, so we log everything as well. We generate ROS bags. Um, this is just essential for operations for our team because, as I said, we only get to see the car and work with the car no more than 4 to 5 weeks in a year, right? So no more than 1.5 months scattered throughout the year. Um, so for the remaining 9.5, 10 months, we rely on all the data that we have gathered. My team has released all of this data open source. There's a data set called RaceCar, which has all the perception and control data from the post IMS race in 2021, not just for my team, but for six of the other teams, including some of the European teams as well, because we want the community to come and take a stab at these challenging problems of detecting an opponent at high speeds. How do you work? How do you avoid collisions? When you are both going 160 miles per hour. And
Sure.
so I think there is a very academic, tangible piece to it. We know that we are competing, and but at the end of the day, we are all in it for the greater good, which is advancing this field together and using it to test the breaking points of all these algorithms that are used all the time in autonomous driving.
Yeah, yeah. So interesting. I mean, and I mean, I so many questions. I mean, which because it's so exciting and
Yeah.
interesting of a problem. But like local, you mentioned localization, for example.
Yes.
Um, so which is figuring out where the vehicle figures out where it is on a map, or on, in this case, on the oval or whatever on the racetrack. How do you is that just, are you just using RTK, or there's some other things that you use to refine RTK corrections for sort of centimeter level precision, or do you need sort of more precision than that? I mean, how much precision do you need, and at what rate do you get it, I guess, cuz GPS can only operate so fast, right?
Yeah. So we I think for majority for the race where we went 184 miles per hour, we were solely relying on RTK as the
Okay.
source of localization. But that being said, we do have some alternate measures in place that we are actively developing. So to answer your questions, the uh, I think the Novatel RTK comes in at 20 hertz, so not terribly fast, but and also when it comes, as you probably know, the solution comes in, and sometimes the solution will not have a good solve quality, so it will have a large standard deviation. So if you just kind of again pipe that through to your fusion algorithm, like we have a nonlinear Kalman filter which fuses everything together, it's not good. Your car is not going to be precisely localized. So we have three different GNSS systems, the vector nav. We rely on not just the RTK correction, we rely on the 125 hertz or sometimes 250 hertz IMU data to feed into the localization as well. Um, but now what we are experiencing, and I think this is honestly a must needed thing for multi-agent racing, is What happens is, I was describing earlier that we have to have software to slow down the car if something goes wrong. So almost every team has the some logic similar to the following: that if you are not sure about your localization or your RTK corrections have stopped arriving because the car has lost internet connectivity, it relies on the internet to fetch these updates. Um, then you should slow the car down, right? So the car will come to a stop. I think this is fine if you are racing by yourself because you don't jeopardize anybody else. But if you're in the middle of an overtake, or if there are 2 or 3 cars on track and the car in front of you suddenly slows down, then it's kind of, jeopardizes a major crash or an incident. And so now my team is also working on, and we have some working implementation where we do SLAM as well. So we localize ourselves based on LiDAR based matching with a map of the track as well. So we can build a map of this Kentucky or Las Vegas Speedway, with some slow moving laps at 40 miles per hour, 50 miles per hour. And then we can localize the car as a source of redundancy, so that even if we don't have to rely on the GPS guards basically at their
Right.
mercy all the time, right? So if and this is also something which is essential, not just because of this redundancy that you shouldn't just stop because you lose RTK, you can continue the race. But in many of the tracks we plan to race in the future, like road courses, there are essentially tunnels and overhead bridges. You will not have GPS or clear RTK all the time. So you will have to have some alternate reliable source of odometry and localization there. So we do fuse SLAM and traditional RTK to localize our car.
Are you using RTK base stations or cellular?
Um, there was a time when we used to have a base station at the track, and I think now we are using. So we don't have our own base station anymore. But at every track we go, like if you go to Indianapolis Speedway, you can pull up this. Our RTK provider is, I think, called SmartNet. So you can pull up their website, type in Indianapolis Speedway, and they will show you where is the nearest base station that they have.
I see.
And it's really like 2 blocks away from the track. So we're like, let's just use this.
Yeah,
So
yeah.
so
Perfect.
the connection is over a cellular signal. So we have a SIM card, LTE connection on the car, and it pulls RTK. That's also how we physically, not physically, like we also have a base station, telemetry station, where we can monitor all the things when the car is doing its practice laps or when we are debugging. Now, in autonomous racing, we cannot issue any control commands to the car, but we can keep an eye on things. And if something doesn't look good, we can let race control know. And race control uses a racing telemetry system by Morelli, and they can issue radio flags to the car. So just like in real racing, you have marshals which are staged at different parts of the track, and they wave yellow flags or green flags to the driver to indicate that use some caution or slow down, or the track is green, or red flag means just stop. In autonomous racing, there is a radio system where race control can issue radio yellow flags, green flags, purple flags to the car to just kind of, control the choreography of what is happening and make the car aware of track situation, especially in head-to-head racing.
Huh.
Yeah, so we do have that level of connectivity, but the car is doing everything and deciding everything to do on its own with the computer on board. It's not listening to
Interesting.
any.
And so in between GPS updates, I guess you must do like basically dead reckoning, right? Or something like the equivalent thereof. Or what do you do? Because I guess the GPS information comes in at 20 hertz, maybe 10 hertz.
Yeah, so this is we rely on a technique called extended Kalman filter. It's a very well established method in robotics, and so you are right. The GPS measurement update comes every 20 hertz, but there is a 125 hertz IMU measurement,
Hmm.
and SLAM will also maybe run no faster than GPS, maybe even a little bit slower.
Right.
So this Kalman filter, it's a nonlinear model of the car. So it provides us with reliable odometry and localization at 100 hertz. Right, we want everything to be as close to 100 hertz all the time as possible. And so in between the GPS measurements, we still have IMU to piggyback off and make some corrections in our odometry. So yeah, I mean, this is basically a filtering algorithm that can you give it a nonlinear model of your robot, and you fuse a bunch of different sensors, and it can provide you with the state estimation at the desired rate.
Yeah. One of the things that we used a long time ago was a fiber optic gyro.
Oh wow!
They're about 10 grand a piece, maybe 15 grand or whatever. But for like it's super precise in terms of like once you have once you know your heading, your the precision of sort of your updates from that point on are
Very
super
nice.
precise. It's very expensive, like I
Yeah,
said,
yeah,
but it might be worth it for
yeah,
is
and you're right. You're right. We are always looking at um, how can we bake in more redundancy, because we are taking a risk. I know there's no driver putting their lives on the line, but think people need to remember that this is a university team. I don't have the same budget as Formula One teams. So it's we have to be very careful in how much risk we can take, and the more risk we can take arises from the same thing. The more confidence you have, which comes from how precise are my sensors, how good are my algorithms. So along the same line, I know there are sensors which is like basically a fancy mouse, because it shoots a laser to the ground and looks at the bounce back of the laser from the ground, but it's maybe just a few millimeters away from the ground. And just like how your mouse can track, it can track the movement of the car. So this is some dynamic sensor, but that's even more expensive, like $30,000,
wow.
$50,000. And
Yeah.
real sort of Formula One teams use this kind of sensors to figure out their model of the car,
Yeah.
I suppose. But yeah, our cars don't have these kind of sensors yet.
Wow. Yeah, I know it can get sensors can start to add up.
Yeah. Yeah.
And then so I guess you mentioned like you want to avoid accidents, and of course, um, what happens? I guess like what are the like what happens to the so is the teams are responsible for paying for the damage to like if the vehicle's damaged, like the team has to pay to fix the vehicle, but then there's also if something happens on the track, right? Is the team responsible for that, or is like sort of the program sort
Yeah.
of
So
insure it in some way?
I think the program has done a good job of shielding us from all the track related logistics. So
Okay.
we have agreements with the Indy Autonomous Organization, and they in turn have agreements with every track, which I think ensure track damage. But if we were to wreck our car, and we have wrecked our car on a few occasions, once quite extensively,
Mm,
um, then the teams are responsible. Then the thing is that um, if you look at the car and think of it as two different things, one is the chassis, the suspensions, the Delara components, and the other is the autonomy part, right? All the main things. So just like how the driver sits in the cockpit, and in the crash, everything else will crumble, but they will be safe. Our autonomy parts will not get usually damaged. They may get shaken up if there's a wreck, but like when we had a wreck at 120 miles per hour at Vegas, the lidars and everything were not damaged at all. The suspensions and the carbon fiber were crumbled. In fact, actually, I have a piece of carbon fiber. I don't
oh
know if it's
wow.
visible. It's on the wall. It's what survived that wreck. But
Mm,
so the theme has always been that the teams bear the responsibility of these Delara parts, of the chassis parts which get damaged. That Indy will not cover.
I see.
But they are supportive. They do provide teams with some kind of crash budget in a year. And they are very, very. I must applaud them. They are extremely efficient in repairing these cars. Like I have seen wrecks on track where I'm like, oh my gosh, I don't think this team can run tomorrow. And then tomorrow morning they're all repaired and the car is ready. So and they have their own engineering team and a racing team, like I said. So they didn't understand these cars really well, the engineering of them very well. They can repair things and swap things in and out. To take us maybe a week to do, they can do it in a couple of hours. Um, so, so yes, we have to pay for it, but I think we are also paying for a lot of this support from their staff, which is much needed.
Yeah. Yeah. Well, I've seen and experienced, you know, crashes in the, in the whole DARPA
Yeah,
realm of
exactly.
things, and I know how like what a sinking feeling that can feel like. And but it's good that you have resilience. There must, and that's what makes this wonderful for the students as well, is learning um you know that failure can be a success. you
Yeah,
know like
100%.
and so, like, what can you describe for me, like, sort of the lesson and the process that maybe some of the students went through when there was that crash, and then all of a sudden, like, how did the resiliency and how to respond to go on to the next stage, like, what was the range of emotions and sort of sequence of events, if you could share it?
Yeah, of course. So I love to share it because it's a very actually interesting trajectory that my team has had in this competition. We emerged as the fastest American team in the first race, so we were riding high. Our
Hmm.
confidence was good, and we didn't win the prize back then. But in my mind, I was like, okay, we went 125 miles per hour. The winning pace was maybe 135, 138 miles per hour. So we were not too far behind. And then you have to understand a little bit of the kind of who our opponents are. So we have teams from Germany, from Technical University of Munich, very established university in automotive engineering. They have an entire department of automotive engineering, and maybe 15 or 12 PhDs who just work on singular things in their stack. Then two other big teams are from Italy. One is from Politecnico di Milano, or Polimu. It's one of the most successful teams in this competition. And then there's another team from University of Modena, which is also one of the top teams. And it- these teams have had basically a head start because they competed in what I would consider as the first attempt towards full scale racing, which in a league called Robo Race. It was mostly based in Europe. It never came to the States in the early days. It ran for a couple of years. I think one team famously crashed right from the start, and it became a meme a few years ago,
Mm.
and everybody started laughing at racing. But anyways, they had like 3 or 4 years of head start working with full scale cars. So after that first race, in my mind, I was like, sure, we didn't win, but if you had to calculate average speed per capita, I was there with five students and myself. We probably won,
That's right.
right?
Yeah.
or
It's a
if
good way
you
to look at it.
calculate average speed based on how many hours have been put into this, probably have won. So that gave us the confidence. We took that confidence into Las Vegas. The race was in January of 2022, and we basically picked up from where we had left. We were in the top four bracket again, trying to overtake other teams. And at the time, and I have no shame in admitting, our algorithms were not, I would say, super sophisticated. So to be very precise, we started off by implementing simpler approaches, which are not maybe necessarily model based and pure pursuit. Just take a trajectory and just steer to keep yourself on that trajectory. And it worked well for single agent, but in head to head overtake, that was a problem. And so, but we still were able to elevate our stack to that point where we could overtake another opponent. And I remember it's the day before race day. Um, we are overtaking the Italian team at 120, 25 miles per hour. And you can see from their camera and from our camera, we overtake them. And then the rules dictate that you have to sort of get back to your line. That's when the overtake is complete. So you close the door, and we close the door too aggressively because it's a banked track anyways, and we just spin out. Like before anybody could realize, the car is just shunted into the wall. The entire left side of the car is damaged, and I'm in pit lane with my students. So these students and I It's funny because our car is going at these hundreds of miles per hour, but we are fixated on this laptop looking at telemetry
Right.
and you can just hear the engine go around the track. And so, well, this was into the exit of the first turn at Las Vegas, and I think my just heart really just sinks at that point because this is the first crash we've had. And up until that point, we were one of the safest teams on pit road. We have had zero crashes, and then we had one of the worst crashes, and so it's disheartening. And we were gutted, and but then, like you said, we the only thing we have is to learn from this and to believe in the science and to parse the data. And so that's what we do. We basically arrive at the conclusion that um, look, we have to overhaul all these simple pieces of the stack and we have to do it right. There are no shortcuts. And these teams are ahead because they started early and they have put in the hours to build these sophisticated models and do this high speed control and planning. And there is really no substitute to get to that point. And we have to just take the bullet and bite the bullet and do it. And so we spend a year, I would say, basically overhauling the entire stack. Not a single piece of code which was used in the first race is on the race car today. Everything was changed. We switched our controller, we switched our planner, and it took us a year and a half. And during that entire year and a half, we were not doing well in the competition at all. We used to go to a race and not even qualify for race day because you need to show some baseline ability for you to race head to head with an opponent. That you can go 240 miles per hour, you can brake safely, you can overtake another car. So, two races in a row for the entire 2022, the first race of the CES in 2023, we used to go there, try to basically, tune our methods, test our methods on track from our simulations. We were also developing these simulators on our own in-house. In my lab here, I have now 6 different simulators that we develop because it's not something which you can it's not available. Right. There's no autonomous racing simulator. So we are developing all of this, and we are essentially making progress, but there are no results on the track for at least 2 years in a row. So it is disheartening, but I have to give the shout out to the students. They are incredible. I have always said our students are among the top talent in robotics autonomy in the world at this point. And every single instance, they have proven us wrong. So yes, from the outside, it must have always looked at, oh, this is like a one trick pony. They had their moment in 2021. Now this team is fizzling out. And internally, we knew that every single race, we were chipping away at the problem. We came in with a plan. Our plan is to test our MPC. Our plan is to test this graph planner. Our plan is to do some head-to-head virtual opponent overtake. We were doing those things. It's just that they were not integrated together. And the moment of integration happened actually earlier this year in January 2024, when we had a head-to-head race in Las Vegas again. And to set the stage, what happens in a head-to-head race is one car is a defender and one car is the attacker. It's like a radio identity of the car. And the attacker will get one lap to do an overtake. The defender can be on their race line. And if you are successful, then the roles are reversed. Then the defender gets an opportunity to do the overtake as well. And if both of you succeed, then the speed at which you have to overtake gets amped up by 25 miles per hour, 10 miles per hour, right? So we start with like 80 and 100, 120, 125. And so this year in Vegas, we showed up and we were confident, but we hadn't really qualified for this ever because we had a crash once and then 2 years we didn't qualify. So I was like, our goal is to qualify this year because we've grinded it. Let's make that as a goal. And, sometimes just you are waiting for something to happen that you don't think of what could happen. That's exactly how Vegas happened for us. Everything clicked. Our integration worked. Our years and thousands of hours that we put into simulation, all the papers we've been writing and the algorithms we've been trying, they worked on the track and they worked like a charm that we became the top seeded team, like
That's
out of nowhere.
fantastic.
Nobody saw this coming, and we became the top seeded team that year. And then we overtook the team from MIT at like 140 miles per hour. That's how the rounds evolved. And then they couldn't overtake us, and we saw ourselves in the finals. And I was like, wow. I mean, that was like that felt like the biggest win in itself. That was redemption for us. Um, and so we faced a familiar opponent from TUM, from the German team, in the finals. And it's almost hilarious but exciting that since we were top seeded, we overtake them at like 100 miles per hour. And then when it's their turn to overtake us, they are about to overtake, but our race car just decides to speed up out of this overtake. And that's like forbidden in the rule set. Right? The rules are such that for safety, the defender has to maintain a constant speed. They're not allowed to weave or accelerate out of the turn. They have to yield. So our car doesn't yield, and then we get disqualified in the finals. So we have to take second place, but that still feels like a huge win because everything has come back together. And so then we are like, okay, surely now we have arrived. Now we are ready. Next race, let's do it. We'll show these Europeans what we are made out of. and and then so we are preparing, but then a new challenge, a new wrench is kind of thrown at us, which is the car has undergone the biggest refresh it has ever gone since the beginning of this competition. So not only are the sensors getting improved, but the drive-by-wire system is getting improved. Like I said, the new motor, the new brake bias. So in retrospect, that's almost like a leveling kind of. It has a leveling impact because all the teams have to reset, and it also brings to light a very real problem in autonomous driving that if you make stuff work on one hardware, it's not a given that it will work the same when the hardware configuration changes. So if you can run, if Waymo can run a Chrysler or a Jaguar I-Pace today, it's not clear can they just run a Ford F-150 with the same prowess, right? So it's a real problem. Again, you have to solve. So we have a new car. It's the AV24, basically a new car. And so the entire summer this year, students and I are living in Kentucky in Indy. We live together in an Airbnb. We basically drive to the track together. We roll out the car. We have a game plan of what we want to do today. And so track time is the most precious commodity in autonomous racing. If you are not making use of your session, which you only get a handful in a day, you are essentially not going to be able to progress. Because no matter how much simulations you do, the track always humbles you. And you learn a thing or two about what you got. And so throughout the summer, we grinded and we tuned our known models from Vegas to the new car. We also made improvements to our MPC. We introduced some tweaks to a model that account for the setup of the suspension, and we will publish that work, because that's part of someone's dissertation as well. And that is what has taken to then finally win this race uh, at IMS in September this year. So it's a long sequence of failures, but this perseverance of the students and just keep at it. These students are like, you are a UV alumni, and many of our listeners who maybe have a STEM education, they can attest that just doing engineering is difficult. It's not like, you show up and you can do everything. These students are doing all of that. They are excelling at all of that, I might add. And on top of that, they are doing nights and weekends on this race car. So as the team principal, as their professor, I have done my best to align these different interests for them. So they do thesis with me. They get credits for their research. They can do their capstone projects. Most of my team is undergraduate students as well. Of course, I have graduate students whose dissertations are directly linked to what they do on the track. So it's really, I want this to be a win-win. And now finally we are seeing the kind of fruits of this labor, because I have many anecdotes from my former students who have graduated that my student was telling me they are at SpaceX giving an interview, and basically they showed them footage of the racing lap and then talked about what they did for the team and how they overcame these problems, because it's problem solving at a next level. And if you are an employer, what more validation do you need for someone's ability to lead and solve problems than basically showing that, look, I took the corner at Indy at 175 miles per hour and breaking a sweat. So it's just truly rewarding for me to be doing this with my students, and I'm always their
Yes.
biggest champion. Yeah.
Well, that's a fantastic story, and the story of persistence again, is a value, and the lessons learned are for the students. I are invaluable. Again, from a employer's perspective, especially at SpaceX, right? Where
Yeah,
they had many issues early on,
exactly.
crashes and what have you, and now they're landing,
They're they're grabbing.
rockets. They're recapturing rockets with big giant robot claws, like from. I
Yeah,
mean, it's amazing.
it
It's
is.
absolutely amazing what's going on, and that's just the spirit of just keep going. You can't be um, at all affected by things that are perceived as setbacks by others. For us, it's just fail often, fail early, right? People in engineering and doing what we're doing.
Yeah, yeah, 100%, 100%. I share that sentiment.
It's fantastic. That's such a great story, and a great one of probably a lifelong lesson for these students that they'll never forget. It's
Oh yeah, yeah, yeah. I mean, I will forever remember the moments when we are at Indianapolis, whether it's the first race or our win. How many computer scientists would be able to claim that they got to kiss the brickyard at Indianapolis? I think that list is very small. So
right,
it's that, it will live with us forever. The bonds these students have built with each other will last a long, long lifetime as well. So yeah.
right. Well, that's fantastic. I mean, the the you mentioned just in terms of now, we talked about the compute power and the sensing and this overtake situation where you kind of spun out. I guess there's obviously path planning of some sort involved with all this. How is you know I guess at 100 hertz or whatever, I guess the path is constant. The path is constantly changing, right? Your plotted path, and I guess based on lidar information and obstacles, you're changing where it needs to go, but you can't change it too dramatically. Do you ever get into this situation where it's a it could be a lose-lose? Like if I correct too much, I'm gonna spin out or I'm gonna roll the vehicle. But if I don't correct, I'm gonna collide. Do you see those situations arising much in this situation in your what you're
Yeah, I
doing?
mean, our goal is to do our best to never get caught in such a situation. But the concerns you raise are valid. So we have a graph-based motion planning algorithm. It's a pretty clever algorithm. Some of it is published as well, and the idea is you have to continuously replan. So in racing, if there is nobody on track, just stay on your race line. Okay, easy peasy. Then the problem is localization and control at high speeds. When there is an opponent in front of you who are impeding your ability to be on your race line, you have to safely figure out a way past them. Um, I say pass them with a caveat because, like I said, in our racing rules for autonomous racing, we impose some sort of artificial limit on the defender. If it was free open season racing, the passing would be very difficult. So it's just early days of racing, so we have some contingency baked in. But even if they are not drastically modulating their speed, they are free to be on any line of their choosing. Okay, so it's not like they are always going to remain on the inside of the track, and you can just pass them on the outside. So then our planner is getting the best estimate of where the opponent is from all of the fusion from our perception. So radar log, camera log, lidar raw, and we predict or we detect where the opponent is to the best of our knowledge. We have to predict what they are going to do. And just within this framework, it's exciting because racing, unlike regular driving, is circular, it's a loop. So you can learn about their strategy lap after lap. And it can help with your prediction of what they are going to do. So it's a problem which is unique to racing, but an interesting problem nonetheless. So we do all of that. So once we know where they are, what their prediction, in our opinion, is going to look like, our planner is constantly replanning to ensure the things that you mentioned, to ensure that we never come within some kind of a safety ellipse around their position. We don't want to risk a collision with them. We will yield to an overtake rather than recklessly risk a collision. That kind of goes down to just risk tolerance and the repair and all that mentality. This is not an algorithmic limit, but the planner has to continuously adjust. And when we make these adjustments, the planner is also aware of the dynamic limits that the car is physically able to do. So the lines that we produce, that we send to our controller to follow, we check them for curvature and lateral acceleration limit and um, distance to opponent. So there's a you can think of it as an optimization which pays attention to, you want to be to your race line, so it incentivizes that. You don't want to be close to the opponent, so it incentivizes that. You always want to have dynamic curvature limits, and you never want to exceed some limits of your tire. So it's an optimization, and we have simulations that we run. And so, uh, as far as I know, we will never produce a trajectory which is not dynamically feasible. The reason we have typically spun in the past is because we commanded some throttle or steering, which made the tires lose the traction. So it wasn't that the trajectory was bad, it's that our ability to take that trajectory and translate that into a safe control command was underestimated. In fact, the at the Indy Autonomous Challenge last month that we won, there was a passing competition, and there is a very interesting moment where my race car tries to overtake an opponent, but there is no gap available. It would have hit the wall, so it slows down, almost like rear ends them, but doesn't make contact, and then goes back the other way and then easily makes the maneuver on the inside. And I think that was a first that we have seen in this competition, that a car didn't wreck a car, it just rear ended a car. It actually avoided a collision at 100 miles per hour. And that's the planner again doing its job, right? And it's knows that this is how fast I can brake, this is how fast I can accelerate, this is where I think the opponent is. They're probably going to be on the outside, and maybe a human driver would have taken that outside gap because there was maybe one car with there, but our car decided to just go on the inside because it was entering this ellipse of safety critical collision. So the planning is where I think the in the future of this competition is going to lead to the most advancements. I think when you have many drivers, and I think you can attest to this as well, the kind of things we are seeing in real world autonomous driving, the kind of failures we are witnessing are either attributed to misperception, that they couldn't perceive the thing accurately, or sometimes they couldn't predict the motion of the agent. So um, prediction is, and every single autonomous vehicle can never really get the prediction of every single agent around it 100% right. So you have to live with the fact that the predictions will never be correct, but can you still plan in a manner that even if there were uncertainties around this prediction, especially in this chaotic multi-agent situation, which is what racing is. Like I grew up driving in India. There's no more chaotic multi-agent driving prediction problem. So that should be the litmus test of how robust is this algorithm. And I'm trying to use racing to basically make the analogy that nobody is saying that you have to speed through traffic to be safe, but we are learning these how to tune these models which are physics based, how to understand the friction limits of the car, which might be useful when the road is damp or there's rain or some snow on the road. So some things that we are discovering and peeling slowly, because it's just a research frontier right now, it's not an industry, I think will have some significant bearing on the safety of regular autonomous driving, which is really what my true AGI interest is.
Yeah, yeah. Well, I mean, and I mean, all this is I mean, it's definitely touches on things that apply, broadly to autonomy, and one of which is redundancy and safety. You've mentioned that some of the things that you have that are redundant with regards to some of the sensing technology. Um, but for fail safety is different from reliability, right? And and remaining operational, as you know. And so, like, on the safety side, um, what is there I guess, what is the is there a fail safe mode of, like, what's the minimal risk condition and situation that this vehicle engages in? Does it just slow down and then stop, or is there like a sudden just sort of braking situation, or you can't do that because you'll spin out? What is fail safety in this kind of vehicle?
So there are all, I would say all failures are not same. So we have tiers of what your response should be based on the criticality or severity of the failure. So obviously, if you for, let's say, you don't have any slam running and you lose all GPS, it would be reckless to remain on track because you cannot localize anymore. Just with IMU, it will drift within a matter of a few milliseconds. So in those kind of situations, when something critical goes wrong, our best uh, thing to do, the minimum risk condition, is come to a gradual safe stop. So we never want to just slam on the brakes. I think the only way we would slam on the brakes is if we were hitting another car because they stopped in front of us and we were coming in hot. Even then, I think my car would actually try to swerve rather than just slam on the brakes. But so any kind of safety critical hardware failure or sensor fault, the response should be try to save your car and come to a stop. There are some kind of faults where it's maybe, we have three lidars for perception. One of them is behaving iffy. We have six cameras and only one of them is operational. Yes, it affects your ability to perceive, but at the same time, it's not, that you don't know anything at all about where the opponent is. So if so, then this can be quantified. This can be quantified by saying how uncertain I am about where the opponent is. If that uncertainty bubble is huge, then I don't want to continue the race because I don't trust my own ability that I'm avoiding them, but actually they're not even there. I'm going off track to avoid them. So, so there is some level of tolerance baked in, which maps some empirically to a failure. In this case, some radar failure or some packet loss failure or bad prediction failure. Those things you can compensate for. And the ultimate kind of redundancy is, and you wouldn't believe this, but this is really what's happening is, if there was some situation where you were overtaking and they just swerve in front of you. So nobody, even a human driver, couldn't do anything. The last resort is that race control can issue something called a purple flag, which will just kill the engine instantaneously. And it will lock the wheels. We know the car will spin out, but they will just try to save the car, last resort. And there have been a few occasions in practice where some teams have received that purple flag because it was clear that one of the cars just wasn't doing what it's supposed to do, and a collision was imminent. And sometimes, the one of the worst crashes we've had in the competition is a T-bone crash between two autonomous cars, because one car was overtaking and it just kind of T-boned into the sideswipe the opponent, which was laterally to them. So, so as much as possible, we don't want to lose control when we brake
So
and
the
come to
purple
the safe
flag's
spot.
kind of like a remote e-stop. That's what
It's
it is, right?
basically that is. It's
And
a
it
e-stop.
cuts the engine and applies the brakes. Is that
Yeah, full
okay?
lock, cut the
Full
engine.
lock.
Yeah, just apply the brakes. Yeah.
Is there and I guess on these tracks but like, I guess it could is I guess the what's the vehicle, worst case, will crash into a wall or go into the field. I mean, is that the worst
Yeah, going
case?
into going into the field is much preferred than going into the wall.
Right.
But even going into the field will damage the front nose cone. The suspension arms will get bent. We kind of forget, like in our simulators, we are like, yeah, we can touch the inside line, but on a real racetrack, I think you will see many drivers, they can sometimes just, hit the curb on a racetrack, which is this bumpy surface. They are hitting the curb because it gives them a faster exit through the corner. If our car hits the curb, it's going to just shake everything up. So we want to stay away. So I know when the motorsport fans look at our races, they're like, "Oh, this is so conservative. It's not taking the race line." Um, so first of all, I think I have to clarify: nobody in pit lane is motivated by replacing human motorsport racing drivers. We are all fans of racing. We are motivated by the algorithmic AI robotics challenge that wakes up every single morning and we make the drive to the track to test our ideas. That being said, our goal is to be remotely as good as the human. But to circle back to what you said in the very beginning, I do deeply believe that because we have these LiDARs and these better sensors, and the human just has the feel and the experience, there could be a time where these cars can outperform human racing drivers. It's not here yet today. It's not here in 5, maybe not even 10 years, but it's possible. That is what the gold standard should be. Even for autonomous driving, I always ask, yes, these cars can drive in the Bay Area or in selective cities. How well are they driving? What kind of mistakes are they making? Are they making the same kind of mistakes that every human makes, or they are making the kind of mistakes that no human would make? Who would you want behind the wheels of a autonomous driven car? An expert driver or an average American driver? So that's why I think this last 10% of autonomous driving is just so immensely difficult to solve for reasons that and it's really one of the most challenging problems we've ever taken on as a species, I would say. It's not just an engineering problem, it really is a problem in advancing artificial intelligence, because driving is uh, a very intelligent task. It's just that subconsciously, so many things are happening that we don't acknowledge the ease with which we drive, that the computer will struggle making sense of all these different scenarios.
So what happens when, I guess, you know, for the future of this, as you've touched on, when these vehicles are able to, because conceivably it's going to happen in however many years, we don't know, um, are able to drive like much faster s- than people, not just casually faster, but just they're able to drive faster. Um, what's that mean for you know race the racing industry, in your opinion?
Um, yeah, I think we are a long way, but if we have to entertain this hypothetical, um, I don't think autonomous racing, at least right now, has the same allure outside of people like me who enjoy the I mean, we do have some broader audience, some people who appreciate the technology, who can see past the perspective and the goal of autonomous racing, like I said, not to replace Formula One or Indy racing. So I think there is a path somewhere, and uh, we have been looking into this to not a fullest extent, but certainly these conversations will happen. Like even for real racing, with human driver racing, their interest is, yes, we want to go fast because that's the spectacle. And that's what demonstrates the athleticism and the adrenaline craziness that these very special personalities possess. But we also want human racing to be safe. Whether we acknowledge this or not, um, there have been fatalities in motorsports, and very young drivers at times have basically passed because of incident on track. Nobody wants that. No fan wants to see that. Nobody wants that. So, could there be a role where if you had technology which is better than the human, it's not assisting the human skill, it's maybe just trying to save or compensate or make it safer somehow? I don't know what the answer there is, or whether or not it's even feasible, but I feel there is some room to embrace some of the learnings from racing in particular. So that's kind of the phase. Um, I think personally, it would be also very, very interesting to pit a human driver against AI race car. And right now, I think many of your the listeners, or even many people who see autonomous racing, they often want to ask, how do you kind of match up against human drivers? And the short answer is we're not as fast as human drivers, but there's a more nuanced answer, which is that our cars are not real Indy cars. So we don't really do apples to apples comparison. So you could compare it to the Indy lights timings. But even there, we have a less powerful engine, less powerful aero. So it's not, we don't really have a baseline whether 184 is how fast a human could drive my car. Right? There's
Yeah.
no baseline. But I don't think that is a kind of the problem. We, by the way, have been approached by racing drivers who want to race against a robot vehicle to maybe show that, yes, 1-0 for the humans, and that's likely going to be the outcome if we do that race tomorrow. um, but I do feel that as AI penetrates the fabric of the society, and it remains to be seen how much of a positive impact that have. I know and I'm aware of all the harms that this technology can have and produce, like with every other technology. But as an academic, as a researcher, I do have a positive outlook that, and in some, it will be for the betterment of society, right? So, and whether that's through autonomous driving or or fulfilling this dream of general purpose robots, which we have been promised since the 60s, but they don't exist.
Right.
And
Right.
so
Where's
so so
R2D2?
yeah, exactly, right? So I think they might, as depending upon how society embraces uh, this this, certainly we this is going to play a pivotal role in our future. I am convinced of that. um, Maybe people will pony up or find a different kind of allure towards watching AI race AI,
Yeah.
right? So that has a very niche, doesn't have the same kind of attractiveness as uh, I'm watching this because these drivers are literally putting their lives on the line and they're doing something that very few people can do on the planet.
Yeah.
But you are taking the physical driver out of the car. But many people don't know that racing is still a team sport. I know the driver is the focal point, but without the assistance of 400 people at Mercedes, the F1 team will not work.
Yeah.
So it is a team sport. And so now there is no physical driver behind the wheel. The team is the driver, right? So it has a different kind of, I guess, appeal to it. But I also fully understand right now it's not for everyone. It's not being projected as a sport. But who knows? Who knows, what the future lies. I'm always excited about figuring out and just playing a role. I think there's a quote which says, I cannot tell you how this will end. And all I can do is show you where it will begin and how you can be part of shaping the future of where it will lead. That's basically my outlook on this.
That's right. That's right. And and there's precedent, right, for this, like, chess get chess, had human against machine. Machines eventually kind of got better, but people still play chess together because it's a fun game. It's a game.
Yeah,
It's not just something that you want to play with a computer, especially if it's just going to beat you. There was Go, which was of course much more
much more.
complicated, right? And then that milestone was surpassed. But then even going back to sort of the physical world, horse racing was a big thing, right?
Yes, yes,
Um,
exactly.
and uh, and of course, vehicles came along. Vehicles quickly beat horses. Hence the horsepower term, right? But
Correct.
vehicles were able to go faster than the horses. But you didn't see horse racing change where they were racing vehicles against horses. That wouldn't be very exciting.
Right.
But horse racing as a sport, because as a mode of transportation has waned dramatically, right? It's just not nearly as popular as it was,
100 years ago.
100 years ago. So, you can imagine at some point, maybe if you project out maybe 100 years, 200 years from now, we as human beings, are we really going to be wanting to drive the cars, because now they're just able to drive us so much faster. They're also able to fly and do everything else, right? So, um, at that point, you know, racing cars will be as antiquated maybe as racing horses is now, right?
Probably, probably.
But yeah, the probably, I guess in my opinion, I don't, there'll be that moment where you'll have man versus machine. You'll have a race car driver racing against an autonomous vehicle just to sort of to prove that it can be done. And then the autonomous vehicle will win. But that's not going to change racing because it's not fun to watch machines race
Yeah.
against each other, right? And as you mentioned, it's a team sport. So, maybe it'll follow that similar path if precedent is any prediction of the future.
Yeah, I think that's a very fair shout. That's likely how it plays out. I completely agree um, to your point that if you dial the clock back to a century ago when we were transitioning from these horse-drawn carriages to basically horseless carriages, there was a lot of skepticism in the public that is this car safe? Is the engine going to blow up in my face? What is this brake? I don't know what the steering wheel is. I'm used to the reins of the horse.
Right.
And so actually motorsport began as a way to demonstrate the performance and safety of these automobiles. That's what the interest of the automotive manufacturers were at the time. It very much later that it grew into a spectacle and entertainment and the sports angle. And I would also reckon that many of the advances we take for granted in our SUVs and sedans, you can trace their origin to some innovation in motorsport, whether it's seatbelts or rear view mirror or a better material for braking or suspensions. So actually, this is why I started autonomous racing. I feel that uh, now we are at the same transition. We are going from driver driven carriages to driverless carriages. So the same questions of safety have resurfaced. Is the AI going to do stupid mistakes? Do I trust this technology enough that I will allow it to ferry my kids to school and back? Many people today would probably be on the fence or even outright say no. And so where is the litmus test, the proving grounds, the motorsport equivalent to show that it can be done? And if you can do it at 150 miles per hour, surely you can do some of that at freeway speeds. Not to suggest that the problem universes are equivalent. They are very different, and there's different problems in perception, especially. But I do feel somehow that this DARPA mentality of the entire industry started. Somewhere along that line, we lost this sort of, constructive pitting things against each other to drive innovation mentality. I think it's still happening at a very different level where billions of dollars have been invested and it's a real high stakes competition. So, but that has its own repercussions on what we see in the AV industry, which has made tremendous leaps and bounds. But I think many people would agree it's not fully solved yet. At least not to the level that humans can solve it. Like I can go to any city and take a flight and rent a car, and it could be whatever model they have available, and just sit in it and drive out. I don't have to relearn how to drive. Maybe I spend 10, 15 minutes familiarizing with the layout of the buttons, but that's about it. I can generalize to different cities, to different hardware, to different countries, left hand drive, right hand drive. So I understand something innate deeply about how the world works. And that's why I feel, I keep circling back to this, but it's the ultimate problem. It's the problem from which we have the most data available for any robot. By some definition, ADAS systems and autonomous vehicles are already the most widely deployed robots in the world. We have the most amount of data for them. So let's try to solve this. Let's try to solve this to say that general intelligence is doable if we can show that general driving intelligence is also doable.
Well, this has been a fascinating conversation. We can talk for hours, and we
Yeah,
probably should. I would love to have another conversation with you if you'll come back when you win your next race. And
sure.
and just congratulations again to you and the students and everybody who was involved because it's really a can be a extremely not just rewarding endeavor, but it's certainly wonderful for the industry and wonderful for the future of this technology. So thank you for sharing in depth your experiences with this. This has just been a fantastic episode. Thank you.
Yeah, thank you so much, Paul, for all the congratulations and the kind words. And I honestly have lost track of how long we've been discussing because, like you said, we both are thinking about these problems very, very deeply on a day-to-day basis. And as I said in the very beginning, it's always just a joy to chat with you, and I always end up learning something. So thank you again for inviting me, and I would love to return in the future for another discussion.
Oh, very much likewise. And thank you so much. I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.